All right, thanks Aaron, thanks Adam for organizing this. It's a pleasure to give the theory tutorial. I should say this is, even though this is the first tutorial, it's not a tutorial about the definition of differential privacy. If you really don't like differential privacy, this workshop might not be the right place for you. But so I've spent very little time on the definition, and I'll focus on some of the algorithmic work that's been done in the theory community, and I want to focus in particular on one theme, which I call privacy by learning the database. And you might say, well, why is that? Isn't privacy intuitively the opposite of learning the database? And yet, what I'll try to convince you in this talk is that you can turn learning algorithms into powerful private data release algorithms. And moreover, I think this is really a common theme in a lot of the theory work that's been done. And this is really what my tutorial is about. And I want to jump right into the first basic model that we're going to look at, which is the model where you have a trusted curator and an untrusted analyst. And the curator has a data set D, which is just, as usual, a multiset over some universe U. And the analyst has a set of queries about the data set that he wants to get an answer to. And the curator wants to give these answers, but he also wants to make them privacy preserving. So what he's going to return is a privacy preserving structure S. This could be a synthetic data set or just a list of answers that is accurate on the queries. Okay, and I'll tell you what accuracy means. But this is the basic model, just two parties, and that's what we'll focus on first in this talk. Okay, and to be a bit more concrete, let me fix some representation for the data set. We'll actually think of the data set as a vector or as a histogram. And if you let capital N denote the number of elements in the universe, then you can think of the data set really as an n-dimensional vector where each coordinate tells you how many elements of type I, or coordinate I tells you how many elements of type I are in the data set. Okay, this is just a histogram, and this will be useful representation for the data set. And in fact, we're going to normalize the histogram so that it's actually a distribution over the universe. Okay, so if it has non-negative entries, if you normalize them so that they sum to 1, then you can think of the data set as a distribution. And this will be useful. Okay, so what are the queries that I want to look at? We're going to look at statistical queries that are also sometimes called linear queries or counting queries. And all that really means is that there are vectors in this histogram space. Okay? And for normalization, we'll assume that the coefficients are between 0 and 1. And let's make it even simpler. For this talk, you can just think of the coefficients as being either 0 or 1. So a query is just a 0, 1 vector in this histogram space. And the answer to a query, which I'm going to denote by Q of D, is just the inner product between the query and the data set, if you think of them as vectors. Okay? And the way we normalize things, the answer to a query is between 0 and 1. By the way, if anything's unclear, I might be speaking different language than some of you, so stop me if something is unclear, okay? Anyway, so these are the queries in the data sets that we're going to look at. And why should we focus on statistical queries? Just one slide. It's basically because lots of data analysis reduces to asking multiple statistical queries, and we can do a lot of useful things by knowing or learning statistical queries about the data set. Here are some well-known examples that were pointed out a while ago. And moreover, you can even, anything that there's this statistical query learning model that was proposed by Kearns, and anything that you can learn in this model, you can actually also implement using the statistical queries that we just looked at. And this model really includes a lot of the things that we can do in learning theory. So these queries are actually very general. Even though they have such a simple representation, they're quite general. So how would we get a privacy-preserving algorithm? Let me jump right into it and tell you about the curator's wireless stream. Okay, so this is what this guy really gets excited about. And it would be something like this. Okay, so he's given the query set Q. And what he really wants to do is he wants to find a synopsis or a structure that maximizes the privacy in some sense and is at the same time accurate on all queries. Okay, so this is of course a completely ill-defined optimization problem because what does privacy mean here? But this is really what sort of intuitively the curator would like to do. Okay? He wants to maximize privacy while guaranteeing accuracy on all queries. And if you see what I mean by accuracy, it really means that you have only an additive alpha error on all queries. And alpha is some parameter here that you can choose. Think of it as much less than 1, because error 1 would be trivial. So think of alpha as 0.01 or even something depending on the data set. Okay? So how do we make sense of this, right? This seems ill-defined and hard. How do we even make sense of this? So I want to propose to try out something easier just for fun. And let's do this. Let's replace privacy by entropy. Let's instead maximize over the set of all distributions over the universe. So S is now a distribution over the universe, just like a data set. So it has the same type as a data set. And let's try to maximize the entropy of that distribution subject to the accuracy constraint. This is now a well-defined optimization problem, right? The entropy is some well-known function. I assume you all know this, a well-known property of a distribution. And the accuracy constraint is formal also. So this is a well-defined optimization problem. Moreover, there is some intuition here that if we try to aim for the maximum entropy distribution that is accurate, in some sense, we give away only very little about the actual data set. So in some sense, entropy is a good first approximation of privacy. Okay? This is the intuition I want to propose here. It won't actually give us privacy in the end. This is not already privacy preserving. But maybe entropy sort of gets us a step closer to privacy. So let's run with this, and let's see where this takes us. And there are actually two pleasant surprises just about this very simple optimization problem. And the first surprise is that you can approximately solve this using a well-known learning algorithm known as the multiplicative weights update rule. So you can solve this effectively. And moreover, you can actually make it differentially private rather easily. Okay? And it'll actually give a great accuracy bounds. So what we did is we sort of derived from scratch, using just intuition, an optimization problem that will give us quite a lot of mileage in the end. So before I explain more about why this is multiplicative weights and why this is, can be made differentially private, let me ask this high-level question: why did learning theorists care to solve privacy problems 20 years ago? Okay, so multiplicative weights is really more than 20 years old. And why did learning theorists bother to do that work for us? And the answer is that they were interested in maximizing entropy because it implies something called generalization. Okay, so and to tell you what I mean by that, let me just on a high level give you sort of the model that you have in learning theory. There you have a learner who tries to learn an unknown concept. Okay, so I'm very broadly defined, an unknown concept. And the only thing he sees about the concept are labeled examples. Okay? So he says, see some set of labeled examples, Q, and only given these examples, Q, he wants to find a hypothesis that is accurate on all the examples that he saw. But not only that, it's not just about being accurate on the examples. That's often not too difficult. You actually want that the hypothesis generalizes. So the hypothesis that you find should do well on unseen examples, things that are not in your example set. And maximizing entropy is one of the principles that ensures generalization. Okay, so this is why learning theorists came up with this stuff. And it actually suggests an intriguing analogy between privacy and learning theory, which I think is at the heart of this tutorial. There's the following analogy. In privacy, we have a sensitive database. It sort of corresponds to the unknown concept in learning theory because we can't access it freely. It's sensitive. We can't just go and do whatever we want with it. In the same way that in learning theory, you can't just access the unknown concept arbitrarily. Your access to it is very restricted. And in fact, in the privacy setting, the only way we're going to access the database is through queries. Okay? So we're going to ask a few queries. And in some sense, the queries are examples that are labeled by the answer on the database. And in this sense, they're really analogous to the examples that we encounter in learning theory. And at the end, in privacy, we want to return a synopsis, that is, an output that approximates the database well on the query set. And this is really analogous to the hypothesis in learning theory, which approximates the target concept, namely what's analogous to the database, on the scene examples. But more interestingly, there's also this analogy between preserving privacy and ensuring generalization. Okay, so in privacy, we sort of want to touch the database only very lightly because we must ensure privacy. And in learning theory, we only want to touch the database or the concept very lightly because we want to ensure generalization. Okay, so this is sort of the high-level analogy that I want you to keep in mind, which sort of explains why learning theory is such a useful tool in coming up with privacy-preserving algorithms. Okay, so this is more of on a philosophical note, and we'll later make this analogy a bit more formal. But for now, this is kind of the philosophical picture. Okay, so let's go back to our optimization problem, which I promised would be very helpful to us. And let's derive from it an actual privacy-preserving data release algorithm. Okay? So how can we solve this problem? First, note that entropy is a concave function on the set of distributions. So we could just hammer this problem using the ellipsoid algorithm. So that's some very general heavy hammer that can solve concave maximization problems. So we could do this here and solve it. But it would give us very little intuition about the problem, and it would also not give us a way to make it differentially private. So we'll take a different route. Okay, and what is the route that we'll take? Well, we look at this optimization problem, and maybe this is something you can already see. What is sort of the first guess that you might have about S? Okay, what is, if you had to start with a distribution, ignoring the constraints, which one would you take? Well, you would take the uniform distribution because it maximizes entropy. It's the unique distribution that has maximum entropy. And so you can start with that and ask, what is wrong with it? Okay, why aren't we done? Why isn't the uniform distribution already what we want? Okay, and the only thing that could go wrong is that it violates one of the constraints, right? So meaning that the uniform distribution does not approximate the actual data set on all the queries. Okay, so if we have such a violation, if we have a query which violates one of the constraints, we can try to fix up the distribution that we have. We can try to go from the uniform distribution to a better distribution. And this actually leads to another neat optimization problem, which is how do we go to the next distribution? Suppose you have a distribution d sub t. So in the first case, that's just the uniform distribution. And you want to go to a new distribution, d sub t plus 1. But you want to, in some sense, minimize the amount of entropy you lose. You want to stay as close as you can to the uniform distribution while correcting your performance on the scene query. Okay? You want that your new distribution, d sub t plus 1, is correct on the query that was previously violated. Okay? So in some sense, you want to minimize the entropy loss. By the way, I should say this is the relative entropy. So this is just, you might know this. You can think of this as a distance function between distributions. So you want to, intuitively, what this says is you want to minimize the entropy loss while ensuring correction, while making sure that you perform better on the scene query. Okay? So this is basically how we're going to iteratively solve this problem. We're going to start with a uniform distribution, and we're going to fix it up. Whenever we find a query which isn't already satisfied or which is violated or which violates one of the constraints, we're going to use this query to go to a new distribution which performs better. Okay, so it would be really nice if we had a closed form expression for this distribution, right? What does this distribution look like? I defined it in terms of this optimization problem, which is, again, a little bit indirect. It would be much nicer to have it explicitly and reason about it. Okay? And that can be done, and this is a bit of a technical slide. This might be the most technical slide, but it's not so important, and it's also not difficult. So if you want a closed form expression for this, you first need to relax it further. This Hardt constraint is kind of difficult to handle. So you're going to introduce a relaxation of this problem where you minimize a weighting of, or a sum of the relative entropy and the constraint. Okay? So some of you might know this is just a Lagrangian relaxation. It comes up a lot in optimization. It's completely standard. But it will introduce this parameter eta. Okay? And this parameter eta sort of controls how serious we are about enforcing this constraint. And we'll typically think of eta as about alpha. Okay, so eta will be typically alpha over 2, our accuracy parameter. But it's useful to have a separate parameter, which controls how tightly do we enforce the accuracy constraint in this relaxation. Okay, and actually, this relaxation, you need to do one more step. You need to replace d sub t plus 1 by d sub t right here to make it a little bit easier. This is just a simple approximation step. But the point here is that you can go from this optimization problem that I had using pretty simple steps to a new optimization problem, a relaxation of the old one, which actually has a closed form expression. Okay, so this line, this new optimization problem that we get, actually gives us a closed form expression for the new distribution that we want. Okay, and to cut this long story short, this new distribution is given by the multiplicative weights update rule. Okay, so the multiplicative weights update rule gives us an explicit way to go from one distribution to the next. And it's defined as follows. And some of you might have seen this, but I'll go over it very slowly. So what does multiplicative weights do? It says that the ith coordinate of the new distribution should be proportional to what it was in the previous distribution, d sub t of I, times some reweighting factor, a multiplicative reweighting factor. So let's think about what this multiplicative reweighting factor actually does. Suppose that, it's kind of annoying that I can't walk around because I have to stay behind this microphone. I can yell. Usually I walk around and. Yeah, why don't Adam, you do the pointing. No.
I'll leave Anna away.
Okay. Adam, please stand on the other side. Can you point at the first case? Point at the first case. Excellent. So the first case that Adam is pointing at so nicely is the case where on the query that we saw, Q, the query that violated a constraint, our given answer, the answer given by the previous distribution, d sub t, is too large. Okay? Does that make sense, Adam? Okay, so the previous query is too large. Our answer is too large, meaning we get a wrong approximation to the true data set. And so we want to correct that. So how do we correct that? If the answer was too large, intuitively, we have too much weight on the coordinates of the histogram where the query is 1. Okay, so remember the query is a 0, 1 vector in the histogram space. So if our approximate answer is too large, it really means that we have too much weight on the positive coordinates of the query. So we want to reweight all the positive coordinates of the distribution by a factor that's smaller than 1. And if you think about it, e to the minus eta times qi is smaller than 1 if qi is equal to 1, and it's exactly 1 if qi is equal to 0. Okay, so this reweighting factor penalizes the positive coordinates if our answer was too large. And if our answer was too small, the case is just symmetric. Things just flip around. You want to sort of penalize the negative coordinates. Okay? And why did I write proportional to? Well, because in the end, you do some reweighting, but in the end, of course, you still want to have a distribution. So you have to renormalize to make it a distribution. But I omit the renormalization factor. So it's just, this is the reweighting. Is this clear, or should I go over this again? I have an example that might also help. So if you think about the distribution that you have, d sub t, in the picture right now it's the uniform distribution, and you think about your real data set, which is this red stuff, it's very non-uniform. So intuitively, the uniform distribution is not a good approximation to a non-uniform distribution. So as you can see in this picture, if we now get a query, Q, it's a 0, 1 vector, and what I drew in this picture is that it has too much weight, or our distribution, d sub t, has too little weight on the positive coordinates of the query. Okay, so these are the positive coordinates, and our distribution does not have enough weight on the positive coordinates. So all we're going to do is we're going to reweight these coordinates. Okay, suppose the answer is too small as a result. because our coordinates have too little weight there, our distribution is too little weight there. We want to multiplicative reweight the coordinates. So we want to penalize the zeros, and we want to reward the ones. Okay, and this is done by the multiplicative weights update. Does that make sense? Okay, so this is, it looks confusing, but it's actually very natural. It's sort of what you would want to do intuitively. Again, this is the multiplicative weights update rule, and we sort of derived it from scratch, but it leads to this beautifully simple algorithm where you just start with a uniform distribution, d sub 0, and this is all you do. This is the entire algorithm. For some number of rounds, capital T, you find a bad query, a query that violates a constraint, and you use that query to perform an update, okay, to correct the performance of your distribution on the current query. This is all you do. And the main question is sort of how quickly do we run out of bad queries? Because you don't want this to go on forever, you want to converge. So the question is how quickly do we run out of bad queries? And the beautiful theory that comes out of this multiplicative weights framework says that you actually run out of bad queries very quickly. So there's a progress lemma which uses the relative entropy. Again, think of the relative entropy as a distance function between distributions. So it says the distance between our true distribution, the data set, and our approximate distribution, it must decrease in every round, in every update round, compared to what it was before, by something that depends on the violation. Okay? So if the violation is large, we decrease the distance a lot. We make a lot of progress. If the violation is small, we don't necessarily make a lot of progress. But if the violation is large, we make a lot of progress. In particular, if the violation is at least alpha, so if we don't satisfy the accuracy constraint, then by putting eta equal to alpha over 2, we get that the progress lemma says we make at least alpha squared over 4 progress. Okay, so if a query is bad, if it doesn't satisfy the accuracy constraint, we make at least alpha squared progress. So this is great because this means we converge. The relative entropy between D and D0, that's what we start out with, that's what we have to fight against, is at most log the universe size. On the other hand, the relative entropy never goes below 0. It's sort of a non-negative distance measure. So this just says, because we make progress whenever we find a bad query, we start out at a moderate level and we can never go below 0. This just means we have a bound on the number of rounds. Okay? So there can be at most t equal to 4 log n over alpha squared update steps before we run out of bad queries. Okay? So this is great. We have an explicit bound on the number of updates that we can make. And if you just turn this around and you want to know what is the error that you can achieve with just t steps, it would be this. Okay? Within just t updates, you can ensure error that is just square root of 4 log n divided by t. Okay? So if you want to have alpha, if you want to have a particular setting of alpha, I can tell you how many steps you need. Or if you want to make a number of steps, I can tell you what alpha should be, or what alpha is going to be. Okay, great. So this is the simple multiplicative weights update algorithm, which we derived very carefully. So what about privacy? Why is this so easy to turn it into a differentially private algorithm? And the reason is that really the only step where we even interact with the data set, with a sensitive data set, is the step where we find a bad query. In all the other steps, we don't even touch the data set. And there are only few update rounds. So in some sense, we don't even access the data set that much. We just make a few, we just find a few bad queries. That's all we do, really. Okay? So, okay, how do we turn this into a differential private algorithm? And just to recap, I'm sure all of you know this definition, but I just want to recall it. So, differential privacy says that if you have two neighboring databases, so two databases that differ only in one element, then your algorithm, which should be randomized, must have almost the same behavior on these two data sets. So, well, you know this constraint very well. But the point here is that the algorithm must be randomized. Okay? So our algorithm so far is not randomized. Right? So there's no way in the world it could satisfy already differential privacy. So we have to do something more. We have to add some randomization to get differential privacy. Okay? And Again, let me just recap. How do you do that? Usually use the Laplacian mechanism, which is, all of you know this. You compute the true answer, Q of D, and then you add Laplacian noise. And I'm recalling this because our normalization is a little bit different. So we're always going to add something like lop 1 over epsilon 0 n noise. And this is going to give us epsilon 0 differential privacy. And the reason is that the sensitivity of the queries under our normalization is 1 over n. Okay. Remember, we normalized the data set so that it's a distribution. And this just means that the sensitivity of each query is 1 over n. Okay, so if you add Laplacian noise of magnitude 1 over epsilon 0 n, then you get epsilon 0 differential privacy. Okay? So how can we use Laplacian noise to make our algorithm privacy preserving? Let's look at the query selection step. How would you select a query that is bad and satisfies differential privacy? You can look at the following plot. You write out all your queries. Let's say there are k of them. And you plot the violation that they have. Okay? You plot the difference between the query on the true data set and the query on your approximate data set. Okay, so you write this out for all the queries, and now you add to all of the queries, you add Laplacian noise. Or to all of these numbers, you add Laplacian noise. And after you add Laplacian noise, you take the maximum. Okay? So keep in mind, we want to select a query which has as large a violation as possible. But we can't just select it because it depends on the true data set. What we're going to do instead is first add noise and then select the maximum. Okay, and it's a very nice fact that is sometimes called the exponential mechanism, that the selected index actually satisfies epsilon 0 differential privacy. So there's a lemma by McSherry and Talbot. And moreover, we don't really lose much compared to the maximum. Okay, so had we just deterministically selected the best query or the worst query, we would have gotten this max term. And what we get instead is the maximum possible minus some logarithmic term in the number of things that we're maximizing over and the privacy parameters. Okay, so yeah. Oh, sorry.
Do we add a dot noise 1 over epsilon 0 to each query, or do we have to add noise in the number of queries?
No, so that's a good point. So because we're taking the maximum in the end, we only have to add noise lop 1 over epsilon 0 n. We don't have to scale it to the number of things. So this is exactly what this lemma buys us.
Maybe you should make clear that people are probably some people may be used to seeing the exponential mechanism formulated differently. And
Right.
If you just call this report noisy max, then you simply need a lemma that says report noisy max is differential.
Right.
Non-differentially
Right.
private. That's what it is, and it works.
Yeah. But is that different from what I said? Or, I mean,
not
You didn't
exactly
go
the
around
opposite.
assigning probabilities to each of these things and choosing according to that probability distribution. You added Laplacian noise to each one and you took the max. That was your
Yeah.
algorithm.
right.
So say so, and then say that that's differentially private.
Yeah. Okay. That was my intent. So.
Incidentally, the noise is not symmetric, it's just exponential, positive exponential.
Yeah. Okay. I mean, it follows by their lemma, but the algorithm that I want to analyze is you look at the violation of each query, you add Laplacian noise to each of these numbers, you pick the maximum. That's a well-defined algorithm. It satisfies epsilon 0 differential privacy. Okay. And moreover, the violation or what we lose compared to the maximum is only very small. Okay. So we only lose very little compared to what we can possibly hope for. So again, let's look at this algorithm. We now do the noisy query selection instead of the deterministic query selection. And also, one thing that should be clear to you is that in the update step, we use the noisy answer. Okay, so we compute the true answer and we also add noise to it. I'm skipping over this, but you will need this too to make the algorithm differentially private. But the main step was to implement the query selection using differential privacy. Okay. And what we get just from essentially the previous lemma is that now each step of this algorithm satisfies epsilon 0 differential privacy. Okay? So not the whole algorithm, but each step of this algorithm, so these two steps, satisfy together epsilon 0 differential privacy. Moreover, we have a new error bound which says that alpha is less than what it used to be plus something that we lost due to the randomization in the query selection step. And this is just the term that came out of the lemma multiplied by t, because that's how many rounds we have. But what I want to say here is that, oops, the error bound didn't get much worse. Okay, it only deteriorated slightly, and we made the algorithm epsilon 0 differentially private. The question that we now need to answer is, what is the total privacy guarantee? Okay, we have an analysis that says the algorithm is private in every step, but what is the overall privacy guarantee that we get? And this is where we use composition theorems. So these are very powerful and beautiful theorems, which say that if you take an algorithm where each step satisfies epsilon 0 differential privacy, and you run this algorithm for t steps, so in some sense that's an instance of t times or t-fold composition. If you do that, then you get two privacy guarantees. The first one, and this is relatively easy to show, is that you get epsilon 0 times t differential privacy. Okay, so this is the most well-known composition theorem in differential privacy. Your privacy loss deteriorates linearly with t. And there, if you allow yourself a non-zero delta, so if you go to epsilon delta differential privacy, you can actually get something much stronger, namely a square root t dependence. Okay, so instead of eating this linear dependence on t, you can get a square root of t, and you also have to get a square root log 1 over delta dependence. Okay, but then you get epsilon delta differential privacy overall for this value of epsilon. Okay, and this was shown by Dwork, Rothblum, and Vadan. Okay, it's a more general composition theorem. So good, we now have everything we need to analyze this algorithm, right? We have an error bound, we have a privacy guarantee, so we just need to see what comes out of it. And this is the most important animation in this talk, so I want you to pay close attention. So again, these are the ingredients. We have the composition theorems, we have a privacy guarantee that we hope to get in the end, which is epsilon delta. We have two parameters to play with. Epsilon 0, our local privacy parameter, the privacy parameter in each round, and the number of rounds. These are the parameters that we can set freely. And we can optimize these bounds as a function of the epsilon delta that we want to have in the end. And we plug it all into our error bound, and here we go. Good. So outcome, some nice theorems. These are the theorems that you obtain from plugging in the optimal settings for t and epsilon 0. And let me start with a theorem that talks about epsilon 0 differential privacy. So the guarantee that we get out of this algorithm, I call MW for multiplicative weights, it achieves epsilon differential privacy with error alpha that is bounded by the following expression. Oh, and I should have put an order here. So there are some constants that are missing. I'm a theoretician, I guess. But there should really be an order of here. Okay, so this is not exactly an inequality. There are some constants that I'm omitting. But essentially, alpha is bounded by 1 over n to the 1/3. So n is the database size, and the error as a function of n is 1 over n to the 1/3. Okay, and it scales logarithmically with the universe size and the number of queries. Okay, but the main point here is that we have the sublinear dependence on n. Okay, and you can get a stronger error bound if you go to epsilon delta. You can get that if you want to have epsilon delta in the end, you can actually get a square root dependence on n. You can get 1 over square root n and a square root log q dependence. Okay, and this is a nice theorem in my opinion because it gives you the optimal dependence on the number of queries in the database size. So you cannot hope to have an error bound that improves over square root log q divided by square root n. Okay, so I find this interesting. We started with this simple optimization problem that just followed some loose intuition, and using a few steps, we derived from it an essentially optimal algorithm. Okay, and of course, all of these are worst-case bounds. So this is not the error that you will always see, but this is the error in the worst case. This is the worst-case bound. Good. So now we have the offline setting, the non-interactive setting. This is what I talked about. I also want to talk about the interactive setting because it's nice and we almost get it for free. where the analyst asks a query and you want to give an answer right away, and then he, adaptively or adversarially, based on the answer to your first query, makes a second query, and so on, and they're k queries overall. So it's more challenging because we don't know all the queries, and we still want to be accurate. And this is what I'm going to talk about next, and we can in fact do this. And I should now talk about some work that, or some references. So this interactive setting was joint work with Guy Rothblum, and this actually introduced this multiplicative weight stuff to privacy. It was the offline setting actually came later in these two papers. But I should say that there had been a lot of exciting work in this area before us, and what I find very interesting is that actually all of these papers also use learning theory. Okay? So learning theory is really the sort of the common denominator between these for these papers. I think that's kind of interesting. So let me talk about the private multiplicative weights algorithm in the online setting, and it's really sort of the most natural extension of the offline algorithm that you could think of. Here's the algorithm. It's again extremely simple. You're given a query Q sub t. So what do you do with it? You check how well it does on your current data set. Okay, so you evaluate the query that you were given on your current approximation. You compare it to the true answer, and if that difference is small, and here I'm using some randomized threshold. So if that difference is less than alpha over 2 plus Laplacian noise, so there's some noisy threshold, but this means that the difference between true answer and approximate answer is small, then I just output my approximate answer. Then I just output the query evaluated on my approximation. Okay, and I'm saying, fine, this is all I do in this case. Don't need to work hard. And otherwise, if I'm not accurate, if there's a large difference, a large violation between the approximation and the true answer, then what do? Well, I perform an update. This is just back to the old case. So I output, but okay, I still need to give an answer, obviously. So because I don't have one, my approximation is not a good answer. So I simply output the true answer plus Laplacian noise. Okay, and then I perform the update. And this is nice because somehow the analyst just kind of for free provided me with a counterexample to my current hypothesis. So I'm learning my own data set as we go along. The analyst keeps giving me queries. Either I do well, or else I learn more about my own data set by performing an update. Okay, so this is the algorithm, very simple. And it's interesting that it achieves the same error bounds. Okay, so the same theorems that you had before, they're true even in the online setting. Okay. The thing that changes significantly is the privacy analysis. It becomes much more challenging. And why is that? So in the offline setting, the number of updates we make, the number of rounds of the algorithm, is pretty small compared to the data set. Okay? If you optimize things in the end, it will always be the case that the number of steps is much less than the database size. So, and because of that, we can just appeal to the composition theorems and say, fine, we get an overall privacy guarantee without working for it. Okay? In the online setting, we have k. So remember, k is the number of interactive queries. We have k invocations of the Laplace mechanism. And every invocation really evaluates the true answer and adds Laplacian noise to it. So we really have a lot more. K could be much larger than n, super polynomial in n. We have many more invocations of Laplace than n. And so the composition theorems do not suggest that this algorithm actually has small error. They do not suggest that we can get the error bounds stated in the theorems, because they would suggest that k has to, or that the privacy loss has to scale at least linearly with k, or as a square root of k. Okay, so how do we do this? How do we get around this? And there's a nice sort of martingale trick. We're going to analyze the privacy loss as a lazy random walk. Okay, so we're going to say that there are a lot of cancellations and there's a lot of laziness in the random walk, and we only lose privacy very, very slowly as we go along. Okay? And so let me make a picture about this. So what do I mean by privacy loss as a random walk? We have some number of steps, k. This is the number of interactive rounds, and I plotted them on the line. and I'm interested in how much privacy I lose. For now, I'm not telling you exactly what I mean by privacy loss, but this can be formalized. So how much privacy do I lose? And the way the analysis goes is that you're going to look at a subset of the rounds. You call these rounds busy rounds, and all the rounds that are not busy are lazy. Okay? And busy rounds are rounds that were close to being an update round. Think of them as being update rounds, but a little bit more. They actually could be close to being an update, even though no update occurred. Okay? So the noise variable came out close to causing an update, even if it didn't cause an update. Okay? But all update rounds are also busy rounds. So I'll say exactly what I mean by busy round later on. But for now, this is only a very small subset of the overall number of rounds, intuitively because it only corresponds to the number of update rounds, and there are a few of them. So what we're going to show is that in the busy rounds, the privacy loss is actually something like a random variable that's symmetric. So it could be either positive or negative. We might actually gain privacy, or we could cancel out the privacy loss that previously occurred. And as we go along, in every busy round, we lose plus minus 1, let's say. And in the lazy round, we lose nothing. Okay? So as we go along, really, our overall privacy loss is bounded with high probability by order of the square root of the number of busy rounds. Right? It's like making a random walk on a line. You go left, you go right with probability half, and you end up only square root of the number of steps away from the origin. Okay? So this is the intuition behind the proof, that we're going to show the privacy loss scales only as a square root of the number of busy rounds, and in effect also as a square root of the number of update rounds. So how would you formalize the random walk? And I won't be able to do all of it, but I want to give you a feeling for it because I think it's a very useful technique. So let's first simplify the setting. Let's suppose the output of our algorithm is actually just 0 or 1. And the algorithm simply outputs whether or not an update has occurred. Okay? So the output of our algorithm is an indicator vector, a 0-1 indicator vector of length k, which tells you whether in round t an update occurred or not. Okay? And the intuition was really that this vector is very sparse. It contains very few ones, just because the ones are only in the update rounds and everything else is 0. So it's a very sparse vector. And we're going to use the sparsity to our advantage and argue that this vector actually satisfies epsilon delta differential privacy. Okay? So this is a simplification. Our algorithm actually does not output 0, 1. It outputs real numbers, answers. But this is a simplification that incorporates most of the difficulty of the proof. So how do we start a privacy proof? Well, there's only one way. You have to fix two neighboring data sets, right? D and D prime. And then you have to look at the corresponding output distribution. So the output distribution of the algorithm on D and the output distribution on the algorithm on on D prime. So you have these two output distributions corresponding to neighboring databases. Nothing much happened so far, but I want to tell you how to formalize privacy loss. So here's an approach for proving the theorem. What we're going to do is we're going to sample a vector, a 0, 1 vector v, from the output distribution p. And then we're going to look at the logarithm of p of v divided by q of v. Okay, so this is how much probability does p give to v divided by how much probability q gives to v. And we take the logarithm of that. This is a random variable because we sampled v at random. And what we're going to show is that this random variable x is bounded by epsilon with very high probability. Okay? And I want to think about this random variable as the privacy loss. So the log of p by q. Okay? This is some measure of how different these distributions are. And there's an interesting fact, namely, if we can show this third point, that x is bounded by epsilon with high probability, then we actually established epsilon delta differential privacy. So this lemma is neat because it kind of gives you an operational way to prove epsilon delta differential privacy by looking at this random variable and analyzing it like a random variable. Okay? So again, this random variable captures the overall privacy loss. I want to think of that as the total privacy loss. And using the rule of conditional probabilities, you can actually write it as a sum over the probability loss in each round. So I want to think of this random variable as the probability loss in each round. And you define it similarly as the probability that the output is v sub t by, under p, divided by the probability that the output is v sub t under q. And you have to condition on the previous rounds. But intuitively, okay, this is just some syntactic trick to write it as a sum of many random variables to capture this random walk behavior. So we can write the total privacy loss as a sum of local privacy losses, as a sum of the privacy loss in each round. And then using this formalization, we can show exactly what I indicated before, namely that if x sub t is 0, if the local privacy, if the round is not busy, okay, if we don't have a busy round, then the privacy loss is identically 0. So this captures this picture that I said, and if the round is lazy, if it's not busy, there's no privacy loss at all. On the other hand, if the round is busy, so close to causing an update, then the privacy loss is strictly bounded by epsilon 0. Okay? Moreover, you can show that the number of busy rounds is at most order of the number of updates. And these are the three properties that will actually completely formalize this intuitive picture that I sketched earlier, and they give us the privacy proof. Okay? More formally, what you will do is you show that given these three facts, you can apply a lemma by Dwork, Rothwell, and Vadan to show that the overall expected privacy loss is very small. So it's linear in the number of updates multiplied by epsilon 0 squared. Okay, so it depends only as a square of the local privacy parameter. So just think of this as being very small. This will be small enough for us. And if we have a bound on the expectation of the sum, that's great, because now this is a sum of many random variables. We can use concentration to argue that it's strongly concentrated around the expectation. Okay, so it is small, the expectation is small. Moreover, the probability that it deviates to the top from the expectation is very small. Okay, so this is the, essentially the privacy proof. There are many more details that I skip over, but this is how you would formalize it. Let me just say how you would define the busy event. It's actually probably what you already think. You look at the difference between the true answer and the approximate answer, and keep in mind that the update condition was just that these two quantities are far apart modulo random noise. Okay? So the difference between them, which I denote by d sub t, is bigger than this randomized threshold. That was just the update condition. So if you plot this, you just get, this is the threshold, this is the difference, d sub t plus Laplacian noise. It looks something like this. This is the threshold alpha over 2. And the busy event is just all the noise values of this Laplacian variable, which would map this, this quantity into this interval. Okay, so if it were larger than alpha over 2, you would get an update. So these are all the noise values that cause an update. And you take a little bit more than that. You take an extra standard deviation. Okay, so this is essentially the privacy proof. This also concludes the online setting. So we have an online algorithm that gives us the same theorems that we had, and it works in the online setting. Let me now sort of come back to the high level and tell you what we can do. Okay? So we saw this algorithm in both the offline and the online setting. What can we do with it? So well, we saw these two settings. Again, it works on every set of linear queries in the offline setting. And it works on every sequence of adversarial or adaptive updates, queries in the online setting. So this is really what you can hope for there. And it comes with nice theoretical performances. So it's nearly optimal in the worst case. We don't know if it's nearly optimal on an instance-by-instance basis, but that's also been studied in the theory community, and I think Sasha Nikolov will give an exciting talk about this at the workshop, maybe Kunal too. So we might have two talks on this question of getting instance-by-instance guarantees in the offline setting at least. So we have strong theoretical performance guarantees for this algorithm. And Katrina will talk about actually what happened when we implemented this algorithm. So this is joint work with Frank and Frank McSherry and Katrina Liggett. So we did implement this and compare it to previous work, but I don't want to say more about this because Katrina is going to give a wonderful talk about this in the afternoon. So you might say, are we done with this? Okay, is this all we need to do? And the answer is no. There's more we would like to do. For example, keep in mind our representation was linear in the universe size, right? We looked at these histograms, and the natural length of this representation is really the size of the universe. And this could be quite big. So the universe size could be exponential in the number of attributes of the data. So if your data set consists of d-bit strings, then the universe size would be 2 to the d. So that can be too large. And the theoretical, or the question that you would like to answer is if you can get polynomial running time. And in general, actually, there are some negative results. For example, if you want to output synthetic data, which is what multiplicative weights does, so your output is just a data set, then you can't do this. There are hardness results which say for synthetic data, you cannot significantly reduce the running time, or you cannot get polynomial in them. And this is true even for simple query classes. And also there's an exciting result by John Ullman that he's going to talk about at his workshop, that recently it was also shown that the answer is no in the interactive setting if you don't want to restrict the query class. Okay? So what can we do about this? And I want to suggest 3 things. The first one I really like is to sort of go beyond worst case analysis. Look for meaningful assumptions on the data, on the queries, on the models. And this is really an interdisciplinary challenge to find good models that allow you to get faster algorithms and practical algorithms. Okay? And the other thing that many of you in this audience are more qualified to do than I am is to design better heuristics, find out what works in practice, and maybe we can also analyze it. Okay? So I think these are exciting directions that I really would love to see more progress on. In this talk, I'm just going to be lazy, though, and try to milk more out of learning theory. Okay? So I'll try to get an approach to getting better running time by getting more mileage out of learning theory. And to get more mileage out of learning theory, what I want to do is I want to return to this high-level picture, our analogy between privacy and learning, which sort of guided the intuition behind the algorithm. And I want to ask if this is just an analogy or if it's actually a formal connection. Okay, can you turn this intuitive analogy between privacy and learning, can you turn it into a formal reduction or an efficient reduction? So that if somebody comes up with a nice learning algorithm that is efficient, we can use that in the privacy setting to get an efficient privacy-preserving data release algorithm. Okay, this would be the benefit of a reduction from sort of privacy problems to learning problems. And there is some partial answer to this question which suggests that this might be possible, and that's shown work with Guy Rothblum and Rocco Servadio relatively recently, where we were able to give one such reduction, which leads to more efficient private algorithms. And more specifically, the informal theorem I want to tell you about is that there always is an efficient differential private release mechanism for a query class Q, provided that there is a certain learning algorithm for a related concept class Q prime. Okay? So I didn't define it, but pack learning is sort of the standard learning model. If you had a pack learning algorithm for a related concept class Q prime, then you would automatically get an efficient solution to the privacy problem for the query class Q. And this interfaces rather nicely with some existing learning algorithms, so we're able to plug in some well-known examples like learning based on polynomial threshold functions as used by Clive and Servadio. So these are papers in the learning community which we can plug into our reduction to get more efficient private data release algorithms. Okay? So let me indicate how this reduction goes. It's really rather simple, the intuition behind it. So again, it formalizes this intuition that the database is really a function which maps queries to answers. Okay? So think of the database D now as a function which takes as input the query set, or a query Q, and maps it to the answer on the data set. Okay? So this is one representation of the database as a function, and once we can think of the database as a function, we can talk about learning that function in a certain way. Okay, so we're going to simplify this a little bit, and instead of talking about this real valued range, we're going to discretize the range using threshold functions. So I define f sub t as just the threshold function, which is 1 if the answer is bigger than t, and 0 otherwise. So it's just a simple discretization I do that because learning theorists like to come up with learning algorithms for Boolean functions. So you can talk about Boolean functions instead. It's enough to learn f sub t for a fine enough net on the real line to get an approximation of f overall. Okay? So you can restrict your attention to Boolean functions. So let me give you the high-level idea how you can turn this into a reduction. Suppose we have an incredibly powerful learning algorithm which learns functions of the form f sub t. Then what we can do is we can generate labeled examples. x1 labeled by the answer of ft. We have ft, right? That's our database function. So we can generate labeled examples that we just stick into this learning algorithm. And we hope that it just spits out a hypothesis that is a good approximation to f sub t. Okay? So if we have a powerful enough learning algorithm for this class of functions f sub t, then we can just do this. And well, what do we get from this? The point here is that if we somehow manage to generate all the labels in a privacy-preserving way, so if all these labels satisfy differential privacy, then just by the post-processing property of differential privacy, the output of this algorithm will also satisfy differential privacy. So in some sense, if you have a powerful enough learning algorithm and you can generate privacy-preserving labeled examples, then you're done. It'll spit out an approximation of this, this database function, and you can learn the database that way in a privacy-preserving way. You get a good private data release algorithm. Okay, so this is the hope, and there are some hurdles here that we can overcome. The first one is that privacy requires noise. Okay, so the only way we can ensure it is by randomization, which introduces noise. But learning theory sort of has often difficulty coping with noise. It makes problems much harder. So the noise might defeat the learning algorithm. And in fact, in our reduction, we'll see how to sort of generate essentially noise-free examples. The other issue is that kind of, what if the learning algorithm comes back to you and says, hey, I want to have n cubed examples, where n is the database size. That's kind of a problem because we don't know how to do that efficiently. We only know how to generate, let's say, n squared examples efficiently using the Laplace mechanism, or really just, let's say, a linear number of examples efficiently before we run out of privacy. So somehow we need to avoid the issue that the learning algorithm could say, well, give me n cubed examples. And we can do that. And the solution is not so difficult, but I'll skip over it. It's some notion of a threshold oracle that we use to generate labeled examples. These are the internals of it. I'll just skip over it. But it accomplishes it, or it overcomes the hurdles that I talked about. Okay, so you can ask this oracle queries to this function, this threshold function, and they'll give you an answer that's either 0, 1, or fail. And you know that if the answer is either 0, 1, it is correct, let's say. And if it outputs fail, then you don't know what happened. But at least it never gives you a wrong answer. And using this threshold oracle, you can generate examples, x1 through xm, by just giving them all to the threshold oracle, getting the answers to all those queries, and then throwing away all the examples that return fail. You don't know what happens on them, but you know that the others where it didn't return fail, they're correct. Okay? So what you do is just you pass on the correctly labeled examples to the learning algorithm, and you hope that there are enough of them, and then it'll spit out a good hypothesis. Okay? So this.
How do you generate the x1 through xm?
It depends on what your learning algorithm works over. Let's suppose you have a learning algorithm, or it depends on what distribution over queries you have. So suppose you're interested in, let's say, the uniform distribution over some query set. Then you would generate the examples uniformly. But if somebody wants a different distribution over a query set, so there's some distributional model on the queries.
So you're assuming some distributional assumption in your
Yeah, that's a good point.
privacy.
That's a very good point, yeah. So what we get out of this is that you get privacy-preserving algorithms that are accurate over distribution over queries. So it's a little bit different. It's a relaxation of the worst-case accuracy problem. You get accuracy over distribution. But you get to specify the distribution, so it might not be that bad.
Similarly to the learning setting, we have boosting from distribution-specific algorithms to distribution-free algorithms.
Yeah, so there's a beautiful paper on boosting and differential privacy by Cynthia Guy and Salil, and that shows you how to go from, accuracy over any distribution to accuracy overall, to accuracy in the worst case on all queries. But it has a running time blow up, which is why I didn't mention it. Okay. Good. So and this threshold oracle, this actually works. This is essentially what we do. It gets around these hurdles. So let me just mention two applications of this theorem. One is to Boolean conjunctions. I'm sure most of you know Boolean conjunctions. Sometimes they're called data cubes or marginal queries, contingency tables. This is what I mean. So you have the universe size is 0, 1 to the d, and you can think of your database as such a table. And an example conjunction would just be how many people are there with a salary above 50,000 and are male. Okay, so this is an example conjunction. These are very useful building blocks that have been studied a lot. And using this previous reduction, we can get, don't read this. Don't read this either. Read this. So 2 to the d to the 1/3. This is sub-exponential. Okay. So if you plug this into multiplicative weights, you would get a running time that's 2 to the order d, and what we get instead is 2 to the d to the 1/3. Okay, so theoreticians like this stuff. Okay, going from exponential to sub-exponential. And so this shows that using the previous reduction, we can actually break this exponential time barrier, at least at the expense of this distributional relaxation that Mike mentioned. So we get sub-exponential complexity. You can also do this for small width conjunctions. Again, you get some improvement over the previous thing, which was d to the order k. We can get something better, so 2 to the square root k. And I should mention there's an exciting follow-up work by Thaler, Ullman, and Vadan, which actually showed that in the case of conjunctions, you can remove this distributional relaxation, and you can get a worst case accuracy bound over all conjunctions with sub-exponential complexity. Okay, and that's nice because they also use the encodings, the polynomial threshold encodings that come out of the learning algorithms that we use. Okay, so this suggests that reductions from privacy to learning might actually be a useful way to get sub-exponential time algorithms or more efficient algorithms. Okay, so let me wrap up what happened in this talk. I started with a very simple intuitive optimization problem, and we derived from it a simple and powerful private data release algorithm, the multiplicative weights algorithm. And we sort of used this analogy between privacy and learning as a guiding principle in coming up with these algorithms. And I'd say that in hindsight, a lot of theory work can be seen as using this privacy learning analogy. And then we saw in the end that actually you can also, it's not just an analogy, you can make it formal and you can use it to get an efficient reduction from privacy problems to learning theory problems. And of course, the question I want to ask to you, this audience, is if we can use these ideas outside theory and in new settings. Okay, so as theoreticians, we've explored them to some extent in some settings, but I really think that this stuff could be useful in other settings that we can't think of, haven't thought of, and I'd like to see some. I'd like to talk to you about that. So if you want to talk to me during the workshop, please do. And this is all I want to say. Thanks.
We've got 15 minutes, basically, and I'd like to invite people to ask questions. So maybe first we'll just take some time for questions, but then talk to each other. I think there's coffee upstairs.
So first, maybe, are there questions for Moritz? Yeah, absolutely.
So, well, certainly it's very convincing that the learning theory is powerful as a source of inspiration for privacy and as a guiding tool. What do you think about the possibility that maybe trying to really reduce to learning problems might be tying our hands too much, in that the access to the database that a learning algorithm has is more restricted than what privacy allows?
Right. Yeah, I think that's a great point that Sally is making. That let me repeat the question. Sally is asking, well, if we rely on this learning theoretic view and accessing the data only using queries and then learning the database in the way we saw in this talk, aren't we tying our hands too much to one particular approach? And I'd say the answer is yes. And it's interesting to look for techniques that are not in this framework. But I would say it's somewhat analogous to the situation in learning theory, where everything you do ends up being in the statistical query model and accesses the data, the examples, only a very restricted way. And so we're in a similar situation, but it'd be very nice to, I agree that there should be ways to go beyond this way of accessing the database. Adam.
So you could also make a case that, like, you could have replaced sort of learning almost everywhere in your talk, except maybe right at the end with, say, convex optimization.
Yeah.
Right?
You can most usually, okay.
And like, say, all these, you know, we took inspiration from, I mean, you didn't, but.
Yeah.
So I guess, yeah, that was my question is, do you think there's mileage to be gotten out of thinking these in the framework of not necessarily of learning per se, but of sort of optimization?
Yeah, so Adam's question is, what do you get out of thinking about optimization instead of learning? And a lot of what I said is also applies to optimization. So that's true. For example, the multiplicative weights framework generalizes to convex optimization, and there's more to be gained by thinking about it as a tool to solve a convex optimization problem. I agree, a lot of learning theory ends up being convex optimization. There are, however, examples which really use sort of statistical queries or more combinatorial algorithms, like the submodular learning algorithm that we used at some point. So these are really more learning theoretic and don't seem to have a lot of convex optimization in them. That's a good question. Yeah? Sorry? Yeah, we're dealing with discrete data. So that's true. You can think about problems over the real numbers. You know, what do you do when your data set is a matrix, and so on. Sometimes you can go to discretization, but that may not always be the best case. So yeah, there's a whole space of problems over you know, when your data is real value. Yeah. So they all depend on the universe size. So that's one disadvantage of using a discretization, because you know, if your discretization is too fine, it blows up the universe and you get more inefficient. So yeah, one thing I haven't talked about, and it's certainly very exciting, is the case where data is continuous and you look at you know, real value learning problems or learning problems over continuous data. Certainly very interesting, and I haven't talked about it.
Is there any generalization of multiplicative weights to that sort of setting? Really private multiplicative weights without privacy.
That's a good question. The question is there any generalization of multiplicative weights to the setting where your data is continuous? Okay. Didn't quite hear that. Yeah, are there more questions? I have an extra slide on more technical open problems if Jerome.
So at the end of your algorithm, going back to the non-interactive algorithm you started with, at the end, what you use as your estimate of the database is the final estimate you get from
That's right.
successive applications of multiplicative weights. And if I understood the analogy, the purpose of multiplicative weights is to resist overfitting relative to your observations. But when you're done, and you've got a certain set of fixed observations that are private, obtained, is that the right estimate to use to answer your queries? I mean, at that point, you don't need the generalization benefit that multiplicative weights gives you, right?
Yeah, so I think that's a very good point. So there's something interesting happening that, well, multiplicative weights comes with generalization bounds or regret bounds. But somewhere in the privacy setting, we don't use that. In the end, we you know, take the last approximation that you've gotten, and this is accurate on all the queries, which is sort of all we wanted. But I agree, there's something more to be gained. For example, if you see queries from a certain distribution, then you could use the generalization bounds to say that actually you also do well on unseen queries. So it's actually multiplicative weights can do something more powerful that in that setting. But yeah, if you only care about accuracy on all queries, then just take the last distribution.
You mean accuracy on all the queries that you have seen?
All the seen examples, right? But I think Jerome is making an interesting point that if for example, you saw example or queries from a distribution, and you stopped at some point, then you would get bounds on how well you do on unseen queries.
That's right.
Which is a nice property.
Modulo
Some simplicity of the.
some simplicity of the query set is some assumption
Yeah.
about
But also, like in some sense, the regret bound that multiplicative weights has is the reason you only need a small number of update steps. For any no regret algorithm, sort of as a black box, you can bound the number of update steps you need using only the regret bound somehow.
Yeah, Aaron is touching on a nice generalization that you can use other online learning algorithms. Multiplicative weights is one of them. You can use others to, and the regret bounds that online learning algorithms come with always give you something in the privacy setting. They always give you a bound on the accuracy. Yeah. Okay, so you want more problems? Okay, so one I really like is, so there are these instance optimal algorithms in the offline setting. Sasha is going to talk about it. I think that's very interesting. But since multiplicative weights has some nice properties, it's worth asking, does it come with some kind of instance by instance guarantee in the offline setting? So can we argue that on an instance by instance basis is close to what you can hope to do on that for that instance? So if it always achieved exactly the worst case bound, that would not be so nice. But there's a lot of intuition that multiplicative weights actually very carefully looks at the queries and even the data set. So there's hope that it, on an instance by instance basis, it actually beats the worst case bound. This is an honor. Adam's taking pictures of my open problem slide.
well,
This is
there's a
great.
reason. We also maybe one thing that should be clear is that these talks are going to be they're videotaped and they'll be available online. So
That's fine.
there's no need for me to actually take a picture, but I wanted to ask you something specific.
Okay. So then we only use the privacy to learning reduction in one direction, the analogy only in one direction. In the other direction, it's much less clear to me. So is it the case that if you come up with a privacy preserving algorithm for conjunctions with a great running time, does it imply something for learning theory? Does it do something that learning theorists don't know how to do? This would explain some of the difficulty that we have in coming up with a polynomial time algorithm for conjunctions, for example. There are also some settings where you don't have running time barriers because the universe size is small, and I like those settings a lot. Cut queries and graphs are an example. Spectral analysis of matrices is an example. I love that stuff, and I think it's great that the universe size in those cases is small. We don't need to, we don't get bogged down by computational hardness too much, and these are feasible settings that I think are nice. And the final one is Adam's favorite question, which is if you can release k-way conjunctions in time polynomial in n, and error that depends polynomially on d and k, but not something like d to the k. So maybe something like d squared times k squared or whatever, but yeah. So this is a great question. We don't know. The best we can do is 2 to the square root k, something like that. 2 to the or d to the square root k is sort of the limit of current techniques. Polynomial n is not yet, we don't have that. So these are some questions. I think Adam is assembling an open problem list which will contain many more. Okay.
Yeah, so let's thank Moritz.
Right. Thank you.